Hello folks, Professor Fiore here. In this video, we're going to talk about different kinds of resistors, what's available to you in other words, and typical application areas. All resistors are not created equal. So, this is one of those things where we make devices, it's a resistor, but there's all of these different sorts of variations, and students very often ask, what's the difference? I've got a carbon composition resistor, a carbon film resistor, a metal film resistor. Like, why are there so many? Well, ultimately, it comes down to the manufacturer trying to make something that's a little closer to the ideal resistor, right? When you look at a schematic, and when you draw something, on a whiteboard, a piece of paper, that thing that you're drawing is an ideal resistor, right? It represents nothing but resistance. But in reality, as soon as we try to manufacture these things, there are secondary effects. There are temperature coefficients. There's issues with tolerance and stability, parasitic capacitance, all kinds of things like this, right? Along with what you might expect. Right? I mean, up front, you would probably expect, well, there's the resistance value and there's the tolerance. It's 10%, it's plus and minus 5%, plus and minus 1%, right? Those are kind of the expected things. And the power is another kind of obvious one. Is it rated for a watt or a quarter a watt, an eighth of a watt? What is it, right? But these other sorts of things like the parasitic capacitance and an equivalent series inductance, they can play a very important role in how well the resistor responds at high frequencies. At very high frequencies, these small little effects that you can kind of ignore, certainly at DC and at audio frequencies for the most part, you can just kind of throw those away. But when you go into higher and higher frequencies, well, you can't ignore them anymore, right? So, manufacturers are out there sort of optimizing their designs, for resistors, right? To meet certain kinds of application goals. The sort of juggling of these parameters to get the best possible resistor for application A is not necessarily the same as for application B. And typically, as an engineer, when you look at data sheets for things like this, the manufacturer is going to kind of clue you in and tell you, all right, this series of resistors that we've made is really designed for application X, and this other series is designed for application Y. And, you kind of go from there, right? You might say, well, I don't really need a particularly accurate resistor. I just need enough resistance for this, current limiter or whatever it is. So I'm just really interested in a low-cost resistor. On the other hand, this might be, super high fidelity audio kind of thing, and you're really concerned with the linearity of it, the stability of it, the noise characteristic, things like this, and you're willing to spend a little bit more for it. All right, that's the sort of kinds of trade-offs you have to look at. But it is interesting in terms of the sort of the physical results that you're presented with. So here's an example of different resistors, and I've got a little ruler down here with inches and centimeters so you can have an idea of the size. Right? What are we talking about? So most of these are through hole, right? Because they've got wires on them, right? We're going to drill holes in a PC board and put these things in here. These are the kinds of things you would expect to see, when you're monkeying around in a lab somewhere. I did throw in one surface mount resistor, which is right here, right? A little tiny square black thing. You can see obviously how tiny it is and why we would use those in modern designs, especially high volume consumer electronics, things like that, where you're trying to get things as small as possible and high reliability, hopefully, during manufacture. Not really practical when you're in lab, though. I mean, you want to have to sit there and get tweezers so that you can pick this thing up and protoboard something, right? So in any case, just running through really quickly here. Right in here we have carbon film. So there's a carbon film, carbon film, carbon film, and some carbon composition. That's these right here. These are very common. Carbon composition typically, in the old days would be 20% tolerance, maybe 10% tolerance. Carbon film these days, 10%, 5%, right? Something like that. And this is, the typical sort of resistor that you would expect that you've probably monkeyed with in lab, with the color code on it and so forth. There's some metal film resistors in here and here, that are higher precision. They superficially look pretty much the same, but typically you might be looking at 1% or tighter. Very often for these tighter precision, the resistance value will be just printed on it rather than using a color code. All right. I also have a bunch of power resistors here of various sizes. So these are power resistors in here, a few watts, a little bit bigger over here. Here's one in a nice aluminum case with sort of stud leads on it. Mounting holes here, right? Put that down. This actually can't really see it too well, but there's little tiny fins on the side, like a built-in heat sink sort of affair. A larger one over here, I think this is a 20-watt ceramic resistor. This big monster in the back, this is actually a dummy load. This is an 8-ohm, 200-watt resistor. And this is what you would use to test things like an audio power amplifier, right? You really don't want to hook a loudspeaker up to it. I mean, it's going to be deafeningly loud if you want to do a maximum output power investigation on it. So we use this, just a big mahonkin resistor in this aluminum case. You can see the leads coming out here, and of course you could attach this to a heat sink to remove more of the power dissipation, more of the heat that's being created, right? So, 1/8 watt resistors, 200-watt resistor, right? The physical size of a resistor doesn't tell you the resistance. The physical size of it tells you what the power dissipation is. There are also some specialized resistors out here, or resistive devices. I've got a resistor array right here. So there's multiple resistors in here. And there's different kinds of connections that they have that you can buy. This interesting looking thing over here is a force sensing resistor. And basically, when you push on this, the resistance changes. Right? That's a fun little device, a sensing device that you can use. And we also have a thermistor, which is a specifically temperature dependent resistance. And I also have a light dependent resistor, a photoresistor, which is right here. All right, so the resistance depends on the amount of ambient light that's hitting it. So those are your choices, right? I mean, generally speaking. Size, power dissipation. That's really the thing to remember there. Okay? All right. So these are obviously designed for different sorts of uses. What are those characteristics, right? I was talking about different characteristics. Okay. How does that relate to these things? Well, let's dive into that. So what we need is a model. Here's our basic model. It's just a resistor, pure 100% unadulterated resistance. Now, I've put a current source in here, and I got a voltmeter across it. If we do a AC analysis on this, we will be plotting the output voltage versus the input current. In other words, voltage over current, which is resistance. I'll be able to plot the resistance of this. It's kind of a sneaky way of getting a resistance plot, basically. All right, so what I'm going to do is just come up here and do my AC analysis, AC transfer characteristic. All right, I'm going to go from 10 hertz up to 100 megahertz because I want to see high frequencies. All right, and off we go. All right, let me bring this down here so we can see it. And what we get, first of all, I'm going to have to change the axis here. By default, Tina sets this up for decibels, which I do not want. I want simple logarithmic. All right, so there's my 1K resistor, right? And notice, look at these frequencies. It's just 1K. I mean, that's what we expect, right? I mean, that's the idealization, right? That's our perfect resistor, all right? Doesn't matter what the frequency is, bunk, it's 1K, okay? That is it. That's it. Done. Works well in our computations. It's very simple. However, not so much in terms of reality. We need a better model. Like what? Well, this is a somewhat better model. It's not perfect, but it's a pretty good model. So here's my 1K resistor. There is associated with it there are connection leads, obviously, and that produces an inductive effect. So I've called that the body inductance, and that's separated out from the lead inductance, and that will depend a lot on the case. So, a surface mount resistor has very, very small lead inductance compared to a through hole, say, quarter watt resistor. All right. There's also parasitic capacitance sitting across there. Okay. Now, the numbers I've thrown out here are kind of, they're not great, right? This is not like a super great resistor. They're not insane. A couple hundred femtofarads, in other words, a fraction of a picofarad would be typical for like a carbon film resistor, something like that. All right. So anyway, given this, I'm going to plot that same thing I did last time. In other words, sort of a frequency response plot, and we're going to see what ends up happening. There's a complex interaction that goes on here. At really high frequencies, the inductive reactance may sort of take over. Depends on what the actual values here for these inductances are and the resistance value. On the other hand, it might work out, again, depending on the values, that this capacitance dominates and it basically shunts the result. And we get a more capacitive result and the impedance decreases at high frequencies. So both of those things are possible. I'll tell you right up front, resistors that are in the like hundreds of ohms, like a 400 ohm, 500 ohm, 1000 ohm resistor, those actually tend to have the most extended frequency response at the high end. When you get particularly large resistors or particularly small resistors, when you're talking, tens of ohms, single ohms, hundreds of Ks, things like that, you start to see the frequency response limitations sort of earlier, right at lower frequencies. Okay, so what we're going to do is we're going to run through a whole bunch of different values of R given these inductive and capacitive values. And for you sharp-eyed people, you've probably noticed a little asterisk over here. What I'm going to do is a little parameter setting thing. Now, if you haven't done this before, in Tina, what you can do is come up to the analysis, hit mode, and you can do parameter stepping. All right, so instead of single, I'm going to do parameter stepping. And I'm going to use combinational. In this case, it doesn't really make any real difference because I only have the one component that I'm going to be changing. All right. And to do that, you would come up and hit this little button. You get the funky cursor. You would select the item of interest. In this case, the resistance. So you just select that. And now I can set up what I want to do. So what I'm going to do is I'm going to start from 10 ohms and go to 100K. That's 5 decades, right? I'm going to get 5 cases out of that. So I'm going to do 10 ohms, 100 ohms, 1,000 ohms, 10,000 ohms, and 100K ohms. So we can see this by factors of 10, by decades, right? That's the logarithmic is going to do that for us. So it's not going to run by a certain number of ohms. It's going to do it by this factor of 10, okay? Great. Now, I'm going to come up just like I did before and do the AC analysis. And same sort of range of frequencies. And looky what we get. Once again, I have to change my axis over here. All right, so there's my 10 ohm, 100, 1K, 10K, and the 100K. Look at what's happening at the high frequencies, right? So my 1K is looking really good. I mean, it's looking flat out to like 100 meg. But, the 100K is diving over here, right? It's starting to decrease its impedance value. So, hey, it looks like maybe the capacitor is sort of dominating in this case. Similar thing is happening with the 10K, not quite so extreme though. And then for the small values, we actually see the impedance starting to increase at high frequencies. So that appears to be the inductance dominating in that case, right? You see just a little bit of a rise for the 100, but there's a really obvious rise for the 10 ohm. And we can look at this in terms of phase response. All right, phase response for a resistor should be 0. If we went back to the original one we did, right, there it is, 0. Bonk. All right, but now, that was for the ideal resistor. But now, we see all kinds of crazy stuff. Okay. All right. So let's just kind of run through this. Let me grab this one up here. That's 10 ohm, right? You can see the phase shifting upwards. What does that mean? Well, that's inductive, right? That's heading toward 90 degrees. So these are sort of taking over. On the other extreme, right, that's the 100K, and this is going negative, so it's actually being capacitive. All right, so if you compare that back to here, right, going inductive, and this one, click on there, come on, going capacitive, right? It's decreasing in its overall impedance. Okay, great. So how does this compare with the actual components that we that we purchase, that we use, that we design with? Let's take a look. I'm going to rerun that just cause. All right, because I'm going to move over here. Let's see if I can. Yeah, I'll just do it like this. Here is a data sheet from a manufacturer, from RCD, that shows their particular resistance, this RCD series CF. And you can see exactly what's happening. Now, unlike what I did, which had all the individual resistors, this is normalized, right? So it's saying 100% of whatever the resistor value is. And we can see what's happening is, right, some of these, like the big resistors, are sort of falling off, right? And then the small ones taking off, going up. But this is essentially what we saw, back here when we did the analysis, right? We saw that same kind of thing. Okay. Matter of fact, I'll just do it again. I'll just flip back and forth between them. All right. Like I said, this is just on one individual kind of a thing. Unlike, flip over here. Let's just push it down, right? It's unlike this. So these are all designed to have 100% of value instead of individual curves, right? But it's showing basically the same kind of thing, all right? All right, kind of stick that down there. So here's another company, right? This is Yagyo. Here's their resistors. Now this happens to be surface mount, so these things extend pretty high in frequency, but it's the same sort of thing, right? Here's the small resistors, and they're flipping upwards. Okay, the inductor's taking off, and the big resistors, they're going downwards. So, we're seeing that sort of inverse case, right? But again, the bigger the resistor is, or the smaller resistor is, the really small ones and the really big ones, we see these frequency deviations occurring earlier, right? It's the sort of that middle of the road, that like few hundred ohms that extend to the highest frequencies, right? Like we saw here, there's the 1K. All right, interesting kind of phase response there. And I have that as well. Let me move this over here. So here's the same kind of curve, right? Well, this is really kind of cool because, these are the plots from actual components you can buy, and this is what our model is showing, right? They're very similar. So, that's great. You really have to like that. So that model's pretty good. It's not perfect, but it's a pretty good model, okay? All right, so let's go back and look at our options, our different kinds of resistors. Now, if you've seen the video that I did on capacitors, there aren't quite as many options for resistors as there are for caps. I mean, there's a gazillion different dielectrics that you can use, but a smaller number for resistors. So the first one is carbon composition. These used to be like #1 use. They've really kind of fallen out of favor. They tend to have looser tolerances, 20% tolerance, 10% tolerance. They're kind of noisy. There's something called excess noise that's over and above the calculated thermal noise, which would be like a best case. So these have excess noise. You got a low noise application, like if you had an audio preamp or something like that, not a good choice. All right. They do have pretty good voltage tolerance, like over voltage tolerance. So they might be used in like protection circuits nowadays, right? They don't have very good insulation resistance either, so that's another downside. So you don't really see these used nearly as much as they used to. Instead, you tend to see carbon film resistors. Right. Widely available, they're relatively inexpensive. You can find these in 5 and 10% tolerances with no problem. Noise performance is better than the carbon composition. All right. They work well, like I said, at higher voltages and temperatures. So it's a good general purpose resistor. But if you want something a little bit better than that, certainly as far as things like its stability, tight tolerance, and low noise, you want to move to a metal film. All right. The construction is actually similar, and the sizes are going to be similar. In other words, if you look at quarter watt metal film and quarter watt carbon film through hole, like axial type leads, they're going to look physically about the same size. All right. They tend to be slightly more expensive than carbon film. That will depend on the precise parameters, just what the tolerance is and so forth. They are not, unfortunately, quite as tolerant of voltage surges as the carbon films are. So they're not perfect, right? But it's a good resistor if you have requirements for low noise, high precision, all right? So I'm thinking, like I said before, like an audio preamp, maybe a filter, a timing circuit. I need very tight tolerance on those things. Okay, similar to the metal film is metal oxide. It's similar in some characteristics to metal film, but not quite as good in other characteristics. It does have good surge capability, so that's compared to the metal film. So that is a plus. And you often see these as sort of a modest power, like not quarter watt, but like you buy a 1 watt resistor or something like that. A little bit bigger than you would typically use in lab. Metal oxide's fairly common, okay? Temperature coefficient is not quite as good as the metal film. That's really the one you want to go for if you're looking for temperature stability. Now, for higher power, you will probably go to a ceramic type resistor. And these can be, 5 watts, 10 watts, 20 watts, 200 watts like that one I showed. So, high power application, high current kinds of things. They will probably require separate kinds of mounting. These are not going to just be, through hole sorts of mounts, because at least not for the really big ones. All right. And for really high power, you're probably going to need heat sinks or maybe even fan cooling, forced air cooling for something like that. All right. Pretty extreme. Wire wound resistors. These can be extremely high precision. They, however, unfortunately have quite a bit of inductance associated with them, and that limits their high frequency response. So they kind of expensive, limited frequency response. They're kind of a specialty device. You don't see them quite as much as you used to, but they still have use. And then at the bottom, I threw in thick film resistors, which is the very common surface mount. So these are very widely used. Physically, they're very small. Their specs, their performance specifications are not quite as good as metal film. So yes, they're tiny and you can, get decent quality out of them. But if you're really trying to push the envelope there for highest possible quality, metal film would really, for many applications, would be the item of choice. All right. So that's what we're looking at for our resistors, right? It's this wide range, all depending on what your applications are. All right. Very good. I hope you've learned something about your resistor choices, narrowed it down for you, made a little bit more sense. And until next time, this is Professor Fiore saying, have a good one.